looking at the relationship between the roots or the solutions or the zeros, whatever you want to call them, of a polynomial and the actual coefficients in the polynomial. Back when we were looking at quadratics, we saw this idea. In fact, that's how we factorise them. We say what adds together to give these two numbers, what multiplies together, the basic idea. And so we found out, well, look, the sum of the roots, so alpha plus beta, always turns out to be minus b on a. And the product is c on a. So that was quadratics, and that's as far as 2 to go. But of course, we look at polynomials up to any order. So let's expand on that idea. Cubics. The interesting thing is that same pattern remains. So the sum of all the roots, but there's now 3 of course with a cubic, is still minus b on a. But notice now b is the coefficient of x squared because a has become the coefficient of x cubed and so on. 2 at a time. So instead of saying product of the roots, we now call this the sum of the roots 2 at a time. So whenever we pick out any particular pair, so 3 possible pairings, alpha, beta, gamma and beta, gamma, but 2 at a time still is c on a. This one will have a product of the roots, which will be 3 multiplied together, and it turns out to be minus d on a. So the pattern continues. We keep going down the coefficients, but you'll notice the sign alternates. So minus plus minus. So if we move to a quartic, so now a represents the coefficient of x to the 4, b is x cubed and so on. There's now 4 roots. The sum of all 4 will still be minus b on a. If I take them 2 at a time, and now there's 6 possible pairings. So that's c on a. So therefore, 3 at a time, I should get 4 possibilities. So alpha, beta, delta, alpha, gamma, delta, beta, gamma, delta. That'll be minus d on a. But now, if we go all 4 at a time, so alpha, beta, gamma, delta, and the pattern continues. We'll go to e on a. That one would be positive. And in fact, we could keep going and keep going and keep going like that. That pattern will be true for all polynomials. Now, as far as extension goes, quartics is about the limit of what we'll end up looking at. But we could generalise, as I say. So if we've got a polynomial equation, we always let a be the leading coefficient, and then go b, c, d to the end of the polynomial and hope the power is not bigger than 26. 1 at a time. Now this notation we can use, certainly when there's a lot of roots, rather than writing all of the roots down, remember capital sigma represents the sum. So you could say sigma alpha, so sum of all the roots, taking them 1 at a time will be minus b on a. Sum of the roots, taking them 2 at a time, so we just write down one of the pairings, so we usually write the logical one, alpha, beta, will be c on a. 3 at a time, minus d on a. 4 at a time, e on a. As I say, we could keep going in that pattern. If it was a pentic equation, then I could have the sum of the roots 5 at a time, and that would be minus f on a. And so on, and so on, and so on. Now, this relationship that we saw in quadratics holds true for all polynomials as well. Remember the one where the common question was find alpha squared plus beta squared? And we say, oh, well, that's alpha plus beta all squared minus 2 alpha beta. Basically rearranging the perfect square formula. That pattern exists for all polynomials. So if you have to find the sum of the roots, 1 at a time, squared. So alpha squared plus beta squared plus gamma squared plus delta squared, however many it has, it will always be the sum of the roots 1 at a time squared minus 2 times the sum of the roots taken 2 at a time. True for all polynomials, no matter what the order is. Alright, let's have a bit of a play. We've got a cubic. We're going to find 4 alpha plus 4 beta plus 4 gamma minus 7 alpha beta gamma. Wow. Let's find them. Alpha plus beta plus gamma, 5 on 2. I don't really need 2 at a time, but you'll notice I'm only doing part A here. I may need it later on, so it makes sense to work them all out. Minus 3 on 2, and alpha beta gamma minus a half. I've got 4 lots of 1 at a time, minus 7 lots of 3 at a time. That's just a substitution question. There we are, 27 on 2. Oh yes, you might recognise this one from when we did quadratics. That was a common one that kept happening, the 1 on alpha plus 1 on beta. Well, for a cubic you'd have 1 on alpha plus 1 on beta plus 1 on gamma. Well, treat it like an algebraic fraction. Get your common denominator. Common denominator becomes 3 at a time. Top of the fraction becomes the sum 2 at a time. So let's sub in those results. Minus 3 on 2 on minus a half, which is positive through. Hang on. That negative sign is not there, trust me. It's not there. How did that happen? Okay. Let's do the square one. So alpha squared plus beta squared plus gamma squared will be alpha plus beta plus gamma all squared minus 2 times sum roots. You can see where using sum notation could come in handy here, because that is going to be a little bit easier to write using sigma notation rather than write out all the possibilities. Certainly when you come to quartics. Do you remember how many was it we had to write out for 2 at a time? I think it was 6. So, save some time. Sub in 5 on 2 squared minus 2 times minus 3 on 2, 37 on 4. So, really similar sorts of questions to what we saw in the 2 unit with the quadratics, just extending it through to other polynomials. Here's one from a very old HSC, 1988. Okay, alpha, beta and gamma, cubic. Bit of a gift question to start off with. They just said, what's the sum of the roots, 1 at a time? But a lot of people got caught out on that, because notice there's no x squared term. So you can imagine a lot of people would put down the answer 3 for that one, because just out of habit they would have gone, I'll grab the next coefficient, put it over 1, but it's actually 0 for this one. 3 at a time. So this is where you've got to start thinking about, is it going to be negative or positive? And I always forget, so I have to go through it and go, okay, so for a cubic it goes negative, positive. It'll be negative for 3 at a time. So minus 1. Here's the reciprocal one. So again, we create our algebraic fraction. Minus 3 on minus 1, which is positive 3. Very good, very good. Positive 3. You might remember these sorts of questions as well, where we have to find the value of one of the coefficients. We're playing with the roots to get that. So it's known that 2 of the roots are reciprocals of each other. We've got to find what that coefficient of x is. K. Alright. Well, if 2 of the roots are reciprocals, instead of calling them alpha, beta and gamma, I'm going to call them alpha, 1 on alpha, and beta. This becomes useful because alpha times 1 on alpha is of course 1. So when I do product of the roots 3 at a time, it's just going to get me beta straight away. 2 at a time could come in handy because 1 will become 1. So let's play around with it. So there's the one I was talking about, 3 at a time. So we now know beta is negative 3. Now, there's 2 ways I could now approach this question. I could find sum of the roots 1 at a time, and that will get me an equation with just alpha. Solve simultaneously maybe with another one to work out k. But I think a simpler way of doing this now is that, hang on, we now know negative 3 is a solution. So I could use my factor theorem. Polynomial negative 3 is equal to 0. So I can sub into my polynomial, and I should be able to rearrange this to get a value for k. So I can combine today's idea with yesterday's idea of using the factor theorems. And eventually, there we go, k is 13. That's probably, I reckon, the quickest way to approach that one. But as I say, there are other ways of doing it, by playing with some of the roots 1 at a time, some of the roots 2 at a time, creating simultaneous equations. 2006 paper. This time, we've got no coefficients. They're just called R, S and T. The 3 zeros, 1 alpha and minus alpha. First part of the question, find the value of R. Alright, well when I look at this question, I notice R is the coefficient of x squared. So it's probably got something to do with sum of the roots 1 at a time, I would think. Sum of the roots 1 at a time is nice, because the alpha and the minus alpha is going to cancel. And it comes out straight away. So there we go. R is negative 1. Negative 1. Next part of the question. Find the value of S plus t. We now know r's negative 1. Here's the sum of the roots 2 at a time. So I've got 1 times alpha, 1 times minus alpha, alpha times minus alpha. That's equal to s. So I know s is minus alpha squared. Then I worked out 3 at a time. That's going to be negative t. So alpha squared is t. And they wanted s plus t. It turns out to be 0. The alternative, so an alternative way of doing that is we could have said r is negative 1, which would fix up the polynomial there. I've only got s and t left. We know 1's a solution, so I can substitute that in, create an equation, and that would get me an expression for s plus t as well. Okay, 4f we'll play with. That ends our look at polynomials.